6.1 is Introduction to Exponentials and Logarithms. Really, all of chapter 6 is exponentials and logarithms. So this section is going to kind of be heavy with the vague idea of what a graph looks like and a lot of definitions, and later on we'll get into solving exponentials and logarithms. But this is certainly a good starting point, and unlike a lot of the chapters we've seen, it's not really going to tend very far away from exponentials and logarithms. So for starters, we can define an exponential function as f of x is equal to a times b to the x, where a is a non-zero real number and b is any positive real number. The reason we don't want a to be 0 is, yeah, I suppose technically that is an exponential function, but f of x is just equal to 0 is a flat line, so you could kind of put 0 in a lot of classifications, and it's not particularly interesting for an exponential, so we just kind of avoid that. And the reason b can't be negative is then we might run into issues of what happens if we're doing a square root or a fourth root. So to avoid that whole headache, we say b is going to be positive. And this is kind of what the standard exponential graph looks like. Exponential functions are usually meant to model things that grow slowly for a little bit and then very quickly. And so that's exactly what's happening in this graph. Is we kind of start with from our horizontal asymptote of y is equal to 0, and then gradually increase until we hit that y-intercept, and then we increase very quickly. And that's what a graph looks like if b is greater than 1. Now, if b is less than 1, and it still has to be greater than 0. So if b is a fraction, 0.5, 0.25, 1/8, something like that, it's the exact same graph, just kind of going the opposite direction. Those tend to be kind of things that decay. We talk about half-life of compounds and stuff like that when we're thinking of b being less than 1. Some additional facts about these graphs: the domain of any exponential is negative infinity to infinity. The range, and this is before any transformation, so again, this is kind of the base case parent function, if you will. If a is greater than 0, it's 0 to infinity, which is what's happening in both of these graphs. If a is less than 0, it's one of these graphs being flipped, so it's negative infinity up to 0. The y-intercept is 0, a, and notice how this is regardless of what b is, which makes sense. B to the 0, well, in fact, anything to the 0 is just 1. So if we plug in 0 into an exponential function, we'll be left with just a. And I've probably already said it twice. This is assuming we haven't done any transformation, so that can move up, down, left, right. But if we have no transformations, you already know your y-intercept is 0, whatever is in front of your exponential function. And then I talked about how the horizontal asymptote is y is equal to 0. And yes, in this case, we're actually not going to ever cross it, but that's not what it's used for. It's used for, again, kind of where does your graph start or where does your graph end. Now, evaluating an exponential. You don't really have to know a whole lot from the section to answer this first question. When you're evaluating anything, you say, okay, what function am I talking about? I'm talking about my f of x function. I'm going to put in 5 for whatever my input is. So in this case, it's x. So to evaluate this, I just plug in 5 for the x in the power. And then 5 minus 3 is 2. 2 squared is 4. So then, skip a line. 3 times 4 gets you 12. More used for if you're going to check something, or if you want to go through and build your graph by painstakingly picking points. It's probably the least difficult, but also maybe the least interesting thing in this section, so that's kind of why I didn't linger on it very long. But one cool thing about exponentials is it is a very applied concept. You do see it a lot more than, say, graphing a rational function that we've recently seen. So in this case, we have a wolf population. We are told that in 2011 there is 129 wolves. In 2013 there is 236 wolves. Develop a model for this scenario. Now, I should have written this in the question. It should tell you develop an exponential model. Yes, we're dealing with population, so exponential functions are the best way to model population, but I should have specified it because you could have just as easily shown a linear model for this situation. Wouldn't have been very good, but it would have worked. So kind of look for that in the question if you're ever concerned of, should I be using an exponential or linear? It should tell you in the question, or you can certainly, if it's for any of our take-home tests, if there's a clarifying question, feel free to email me, and that's definitely a question I would say, yeah, do an exponential. I won't tell you how to do the exponential, but I will tell you to build an exponential model. Okay, so in order to build a model, I need to have some points to build around. Doesn't really look like I have points. It looks like I have a bunch of dates in this question, but hidden in those dates are actual points. So my model starts in 2011. So if I'm going to have a point, my first value is going to be time, and the second value is going to be the number of wolves. So in 2011, I had 129 wolves. So when I started year 0, I had 129. And then I look at 2013, well, that's 2 years past my start date, and I had 236 wolves. So my second point is 2, 236. Again, I'm not using 2013. I'm using the fact that since 2011 is my start date, 2013 is 2 days after it, that's my second point. You could do it the other way. Again, the model's not going to be as good, but you could have done your first point as 2011, 129. The math would be also a lot harder to deal with. Okay, well, I know an exponential model is f of x is equal to a times b to the x. That's the formal definition of before. And now we kind of have to find our a and our b. And it seems like it's a little bit more difficult, possibly just because we saw the definition. But this problem we've actually seen before just with a line, y is equal to mx plus b. If it wasn't in this course, it was probably a course before this for you guys. And we solve that equation by saying, okay, if I want to solve my m, or more specifically, if I want to solve my b, I plug in a point and solve for that value. So in this case, I'm going to do just that, but I'm going to use take advantage of a quality of exponentials that we saw in the last slide, of that any y-intercept is going to be 0, a. Well, I have my y-intercept here. It's 0, 129. So my first step is just to replace a with 129. And now my second step is kind of what I was getting into. Now I'm going to take my second point. I'm going to plug it into this function. I'm going to solve for b. So my f of x will become 236. My x will become 2. And then you just have to go about solving for b. Divide both sides by 129. I don't know why I wrote that twice. Square root both sides. And so b is approximately 1.353. Now my model is y is equal to, or f of x. F of x is equal to 129 times this b that I found, 1.353 to the x power. And that's usually what a question like this ends, is it asks you to build your model, call it a day. Well, usually kind of the natural next step in a question like this would be like, okay, great, you built your model. Now tell me how many you would predict in the future. So we're going to do that. We have our model. I'm asked how many wolves will there be in 2018. Well, I know, again, my start date is 2011, so I'm going to use my model and plug in 7 for my x. 2018 is 7 years past 2011. And then I just go ahead and evaluate like I did on my last slide, and I would find that I get 1070.72 wolves. Yeah, you could argue you can't have 0.72 of a wolf, so you could say 1071, but I would also counter that this is a mathematical model, and sometimes it's a good idea to leave it unrounded and say, yes, I know that's not possible, but this is what my model is saying, so take with that what you will. Maybe round down, maybe round up, maybe don't round at all. Now, kind of to remove the fluff of the word problem and just get down to a straight up question. I have 2 points. I want to find my exponential model. Well, oddly enough, the word problem in this case was the nice case, because I had a starting point, which means I could use the exponential function to just go ahead and say, oh, I know what my a is, and then go about solving for b. In this case, I don't have my y-intercept. I don't have an x is equal to 0. So instead, I'm going to have to write down the exponential model twice, that f of x is equal to a times b to the x. except for since I'm writing it twice, I'm going to plug in both of my points. So if I plug in my first point, 1 comma 6, into that exponential function, my f of x becomes 6, my x becomes 1. So I have 6 equals a times b to the first. And then I do the exact same thing with 3 comma 54. My 54 will be my f of x, and my x power will be 3. And now in this case, order doesn't technically matter. I recommend always saying whatever the highest power is, you put that above the lowest power for this next step. Now, while I don't know my a, I have two separate equations, and when I have two separate equations, two variables, I try and shrink it down to one equation. So I'm going to do that by actually dividing the second question from the first question. So that's kind of where that setup becomes important, because if I divide this out, then 54 divided by 6 gets me 9. A's will drop out, which is really great because we only want to solve for one variable for now. And then I'm left with b to the third minus b to the first is b squared. You kind of subtract the two. We'll talk about that more later, but I feel like that's reasonable at this point to assume that if you have something to the third power and you're dividing it by that thing itself, well, that leaves you with two of them. And now I just square root both sides. B is equal to 3. And yes, b is equal to plus or minus 3 in general, but we're dealing with exponentials, which means we can't have negative b's. Well, now I still have to solve for a. I want to find my exponential model. I want to find some sort of f of x is equal to a times b to the x. Well, since I have my b, I can go back and pick either of my starting equations and solve for a. In this case, the second equation is much easier than the first. So I'm going to plug in b, or 3 for my b, and 6 is equal to a times b to the first. So I get 6 is equal to a times 3 to the first, which is just, 3 to the first is just 3. So 6 equals a times 3, divide both sides by 3, a is equal to 2. Now, what tends to happen with questions like this is people get to this point and they say, okay, I did a lot of work, I found my a, I found my b, great job me, and move on from the question. No, the question's asking you to write an exponential model, so at the end of the day, you need something like f of x is equal to something. So we're going to plug in our a for the exponential model, our b for the exponential model, and we'll be left with y is equal to 2 times 3 to the x. Or if you want to, f of x is equal to 2 times 3 to the x. If it seems like you're confused where this equation keeps coming from, I mentioned it, I'll go back to the slide right here. So if you're looking at the top middle of the slide, it's that exponential model, that's the standard. The f of x is equal to a times b to the x. So that entire slide we just went through all revolves around that equation. That's how I built it. That's where I plugged my points into, and that's where I eventually put my a and b to get the final result that we saw. That guy. Compound interest formula. This is a little bit unrelated to what we're doing. Yeah, it is technically an exponential model because I have a b that's positive and I have an initial amount that is 0, but we're probably only going to talk about the definition, what it means, and then maybe do one question. So I would say that maybe the first couple slides in this lecture are kind of more important than what you're going to see now in the next slide. But compound interest is very applicable, so it is worth going over. So this is the formula. The formula is probably meaningless if you don't know what the variables are, and that's true of almost every formula. So let's define the variables. A is your account balance. So for example, compound interest, you may have already thought of this. This tends to be used in like bank situations when you're trying to figure out how much you'll have in your account after a while, or how much you'll owe. And so that's the account balances. After a certain amount of time, you have this in your bank account. Your T is time, and that's always going to be in years. So if they give you something weird like months, you might have to do a small conversion, but that's doable. Your P is called your principal, but that's also just your initial amount. It might be PLE, principal PLE. I'll look it up later. But regardless, it is your initial amount. So again, if we're going to go to the banking situation, it's what I would go and deposit on day one. I would deposited $30, some time passed, and then my account balance would be how much I could take from that account, maybe like 3 years from now. R is your percentage rate, or if you watch a lot of car commercials, they call it your APR. That's because it is your annual percentage rate. So that is kind of tied to the reason why we use years for time versus months or anything like that. And then the N is the number of times compounded per year. And typically that is monthly, like if you're doing rent or most car payments or paying off some sort of loan, but that doesn't have to always be the case. You could have it compounded weekly, you could have it only being compounded yearly, and so N is just, if it's weekly, for example, N would be 52. It's how many times it happens in a year. So to see it all in practice, instead of just kind of staring at a weird formula with a lot of letters flying around. If I invest $100,000 at 12%, that is compounded weekly, what will the investment be worth in 30 years? So really all this question boils down to is, can we identify the pieces of information? Can we throw it in that weird formula that we saw in the last slide? And then can we just pretty much plug it into our calculator at that point? So that is the formula. I just brought it from the last slide over to this one. I know my principal is how much I started by started by depositing into my account. So my P is 100,000. My rate is the percentage, should be represented as a decimal, so it would be 0.12. Compounded weekly, I mentioned in the last slide, there's 52 weeks in a year, so N is 52. And my investment will be 30 years. So to put that all together, A of 30 is just me formally writing how you would do the function notation. Really, the important part of this question is that I put all of those things in the place that I mentioned. And then from there, it's just evaluate. I wouldn't even expect you to do this on pencil and paper. I would very much expect you to use some sort of calculator to crunch the numbers, because that's exactly what I would do. And so I'm not going to go through that step by step. The only thing I will say is be very careful if you're using a calculator, how you're doing your order of operations and how you're using your parentheses. So if we wanted to go through order of operations, I would figure out what's inside the parentheses first. I would take that to the power of 52 times 30, and that power should be in parentheses, and then I would multiply that all by 100,000. But if you're good with calculators, honestly, you could type this in just as I have it written down, and you should get the same answer as me. And typically, you might get something further than 2 decimal places. Usually you round up. You could round up 1 cent or down 1 cent. It's one of those, like, are you drawing money out from a bank? They're probably rounding down. Are you paying off a loan? They're probably rounding up. So I'll account for that if I'm grading your tests or your quizzes, or you don't have quizzes, your in-class assignments or anything like that. Okay, so that was more of the nicer case of using compound interest formula. You find all your information, you throw it into your calculator, and you call it a day. Or in this case, we are given very similar information, and we are going to still use that formula, so I'm going to pull it over on this slide. But in this case, I'm told that I want to have a total amount of $40,000 in my account. So my A is 40,000 now. I know my rate is 6.6%, so that would be 0.06 as a decimal. I know I'm compounding quarterly, so that means that's going to happen 4 times a year, so my N is 4. And I know my time is 18. So I'm going to throw that all into my formula. Everything's been replaced other than P, and now my goal is to go about solving for P. So what I did when I solved this is I kind of resolved the parentheses. So again, using order of operations, I did 1 plus 0.06 divided by 4, close my parentheses, take it to the power of 4 times 18. Be careful about parentheses in the power. That's where a lot of the mistakes come from. And that if I evaluate that, I get 2.1292. I divide both sides by 2.1292, and I'm left with my P is equal to $13,693 approximately. That's probably fairly rounded. So now if I really wanted to check my answer, I could just plug in my 13,693. I should be able to use the exact same information that I had other than my 40,000, and then I just check to make sure that it is equal to 40,000. That's a great way to kind of, even in the last question, kind of compare your work, because like I said, this problem, as far as the mathematical sense go, isn't super difficult. It's just there's a lot of evaluating. There's a lot of things that can go wrong in your calculator, and so it's a very good idea in this case to go through and check your answer. Not a lot of effort, very doable. That's the end of this section.